tool of man. We use it constantly to turn night into day with bright lights and to turn winter into summer with its warmth, to communicate and to travel to faraway places. Electricity runs children's small toys and man's great machines. In short, it supplies us with power, light, heat, communications, and transportation. Since an aircraft is dependent on electricity for many of its functions, it is necessary for the professional aviation technician to have a good understanding of its basics. This introduction to basic electricity is presented by the Aviation Maintenance Foundation to help promote safety in flying through proper maintenance. In Part 1, we will discuss the basic principles of electricity, basic electrical laws, electrical circuit arrangements, and direct current measuring instruments. Part 2 will be concerned with alternating current and electrical circuit components. As A&P technicians, we are familiar with mechanical and hydraulic principles which are governed by the basic laws of physics. Electrical principles follow these same basic laws. Although most of us think of Benjamin Franklin as the father of electricity, we find mention of it by the philosopher Thales as far back as 600 BC. Franklin's kite experiment led to the assumption that current flowed from positive to negative. This false assumption theory was refuted with the discovery of the electron. Actually, the particles which move in an electrical circuit are the electrons, which being negatively charged, flow to the positive pole. To understand electrons, we must realize that all matter is made up of atoms. Similar to a tiny solar system, the atom has a nucleus of positively charged protons and uncharged neutrons. Negatively charged electrons, held by a strong attractive force, circle this nucleus. The centrifugal force of the spinning electrons exactly balances their force of attraction for the nucleus. The protons and neutrons provide the weight and the positive charge of the atom, and the negative charges of the electrons exactly balance this positive charge. The mass, however, of the proton is 1,847 times that of the electron. So obviously, for the same charge, the electron is much larger. Different materials have differing numbers of protons, neutrons, and electrons in their atoms. When there are many electrons in one atom, they orbit in several rings or shells. Now, the outside ring, called the valence ring, is the one which contains electrons that can be released to flow in a circuit. In some materials, called insulators, the attraction of these valence ring electrons for the nucleus is so strong that they can be forced out only by a strong electrical pressure. Most metals are called conductors because their outer ring electrons are held so loosely that a small amount of pressure will cause other electrons, those from an outside power source, to swap out with those in the metal. When an electron leaves the power source and joins the outer ring of an atom in a conductor, that atom is unbalanced and releases one of its own electrons to the outer ring of the next atom. Now here the displaced electron joins and kicks out another electron, sort of a domino effect. This is electron flow, or current. Electron movement takes place at the speed of light and continues as long as there is 1. A difference of electrical pressure, 2. A conductor joining the area of pressure difference, and 3. A return path for the electrons. Question: are all electrons involved in the flow of electron current? No, only those in the outside or valence ring. Electrical energy exists in two forms: current and static. If an insulator is rubbed by another non-conductive material, electrons will transfer from one to the other, and a condition of charge will exist. This may be neutralized by contact with a material having an opposite polarity, or by connection through a conductor to the oppositely charged material, or by a spark jumping the gap between the materials. The most familiar form of neutralization is the good zap we get when we slide across the car seat and touch the door handle. Static electricity must build up to a voltage high enough to pass off through one of the three neutralization methods. Large and smooth control surfaces will store huge quantities of electrons, so static dischargers having sharp points may be used to dissipate the charge into the air before it can cause radio interference. Flexible, conductive bonding braids connect control surfaces with the main structure to neutralize the static charge that builds up as air flows over the surface. While static electricity is essentially bothersome, current electricity works for us, and the study of electricity is basically the study of its flow. Throughout this presentation, we will consider the actual flow of electrons as going from negative to positive in the circuit outside the power source. This direction, incidentally, is against the arrows in semiconductor symbols. Electrical energy may be obtained by converting other forms of energy into electricity. Forms such as friction, pressure, heat, light, magnetism, and chemical energy. Static electricity results from friction, as when sandpaper is rubbed over a wing, or air flows over the airplane. An electrical pressure difference is thus built up between the airplane and the ground. To prevent unwanted sparks, a ground cable must be connected between the airplane and the ground to allow electrons to flow and neutralize the pressure difference. Magnetic force is generated by the electrons orbiting in their atoms. Lines of magnetic force occur which produce electrical pressure and attract metals containing iron. When electrons flow in a conductor, these lines of magnetic force, called flux, encircle the conductor. The intensity of these lines of flux may be increased by forming the conductor into a coil. By concentrating the flux with a soft iron core, or by increasing the current through the coil. Permanent magnets retain their magnetic characteristics after the magnetizing force is removed. In materials containing iron, millions of tiny magnetic fields are in a state of disarray and cancel each other. But if magnetizing force is applied to the metal, the individual fields or domains then line up and cause the metal to have the characteristics of a magnet. The ability to retain magnetism is known as the retentivity of the material, and the relative difficulty with which these domains may be aligned is called reluctance. Normally, the more difficult a piece is to magnetize, the better it retains its magnetism. Soft iron has a very low retentivity and is seldom used as a permanent magnet. Anytime a conductor is moved in a magnetic field, an electrical pressure is generated which causes electrons to flow within the conductor. The amount of pressure is determined by the rate at which the lines of force are cut. Now, this in turn is dependent on the strength of the magnet. the speed with which the magnet is moved, and the number of turns in the conductor. Electrical pressure may also be generated by chemical action. When materials having different electrode potentials are immersed in an electrolyte and joined by a conductive path, electrons are caused to flow. This type of electrical generation is discussed in detail in the AMFI course on aircraft batteries. Heat is another force from which we obtain electrical energy. It causes electron movement to speed up, and when certain dissimilar metals are joined into a loop, there will be an electrical pressure difference between the two junctions that is proportional to the temperature difference between the junctions. Light, another form of energy, will release electrons from a photoemissive material and generate an electrical pressure that can force the electrons to flow in a circuit. Quartz and certain other crystalline materials will generate an electron pressure difference between their surfaces when they are squeezed or bent. Now, this form of generator is commonly used for phonograph pickups and in aircraft radios for precise frequency control. Question: name 6 ways electrical pressure may be generated. By friction, magnetism, chemicals, heat, light, pressure. Until we can assign names and numbers to our knowledge of electrical energy, this knowledge can be of little use. The coulomb helps us start our naming process. 1 coulomb is equal to 6.28 billion electrons. Now that's quite a number, isn't it? When 1 coulomb moves past a point in 1 second, 1 ampere is flowing. Electrical pressure is measured in volts. 1 volt of pressure will force 1 amp of flow through 1 ohm of resistance or opposition. Several terms may be used to describe electrical pressure. Electromotive force, EMF, is considered to be generated by some form of electromagnetic generator. Potential or potential difference is voltage by static or chemical means. And IR or IR drop is a pressure difference caused by current flowing through a resistor. Some of the voltage is dropped across the resistor. Opposition to current flow is measured in ohms. 1 ohm is the resistance that would generate an electrical pressure of 1 volt for each ampere of current flowing through it. The opposition or resistance offered the flow of electrons by a conductor is determined by its length, its cross-sectional area, the material from which it is made, and its temperature, and is expressed in ohms. Basic units are often too large or too small for handy use, so metric prefixes are used. A microunit is 1/millionth of the basic unit. A milliunit is 1,000th of the unit. And the prefix kilo means 1,000 units. And mega, 1 million. Question: how many millivolts are required to make 1 volt? (1,000 millivolts equal 1 volt. Electrical problems may be solved because the electron in a circuit follow certain definite and predictable laws. One of the most fundamental of the laws of electricity is that stated by Simon Ohm on the relationship between pressure, flow, and opposition. The voltage caused by a flow of electrons is the product of the amount of flow and the opposition. Now in symbols, this is E equals I times R. Using this law, we can find current in a circuit by dividing the voltage by the resistance. Now as a formula, this is I equals E divided by R. When 1 amp of current flows through a resistance of 1 ohm, there will be 1 volt of pressure difference generated. Simple Ohm's law problems may be solved by visualizing a circle divided so that the top, representing voltage, equals the bottom, current and resistance. With this, we can see that E equals I times R, I equals E divided by R, and R equals E divided by I. Power is the desired end result of an electrical system, and there is a relationship between mechanical and electrical power. 1 amp of flow under a pressure of 1 volt will produce 1 watt of power, often felt as heat. 1 horsepower equals 746 watts of electrical power. The same type of circle arrangement we use to visualize the voltage-current-resistance relationship may be used with power, voltage, and current. Power equals voltage times current. Current equals power divided by voltage. And voltage equals power divided by the current. Kirchhoff's voltage and current laws are basic statements of circuit behavior. His voltage law, in its most simple form, states that the sum of the voltage drops in a series circuit is equal to the applied voltage. Kirchhoff's current law, in its pure simplicity, illustrates the fact that the sum of the current leaving a junction is the same as the current arriving at that point. Practical applications of Ohm's and Kirchhoff's laws require that the components be put into electrical circuits, which, with few exceptions, can have all of their resistive components reduced to a single equivalent resistor, and voltage, current, and power problems solved by Ohm's law and checked by Kirchhoff's laws. Now let's look at some simple series and parallel arrangements. All electrical circuits must contain a source of electrical energy, a load to use the energy, and conductors to join them. In a series circuit, there is only one path for electron flow. The current will be the same through all components. And the sum of all the voltage drops equals the source voltage. The total resistance is the sum of all of the individual resistances. In a parallel circuit, there is more than one path for electrons to flow along. The voltage is the same across all of the components. And the total current is the sum of the current through each path. The total resistance is less than that of the smallest resistance. Complex circuits must be reduced to a single circuit before they can be solved. First, combine parallel resistors R5 and R6. Now, combine this equivalent resistance in series with R4. Combine series resistors R2 and R3. And then combine the parallel combination R23 with R456. Finally, when you add the resistances R2, 3, 4, 5, 6 with that of R1, you get one resistance that is equivalent to all of the circuit resistance. After using Ohm's law to find the voltage drop across each resistor and the current through it, the power dissipated in each one may be found. The total power, E total, times I total, must be the same as the sum of the power dissipated in all of the individual resistors. In order to work with an electrical circuit, we need tools, specifically voltmeters, ammeters, and ohm meters. Most indicator-type measuring instruments use a D'Arsonval or Weston movement, in which the current to be measured flows through tiny hairsprings into a coil, which is suspended in jeweled bearings and is free to rotate. The electromagnetic field produced by this coil reacts with a strong permanent magnet field and produces pointer rotation proportional to the amount of current. Voltmeters are placed in parallel with the voltage to be measured, and because of the extremely small current required for the meter, a multiplier resistor is placed in series with the meter movement. The sensitivity of a voltmeter determines the resistance of the multiplier. Meters such as this one require only 50 microamperes of current for full-scale deflection of the pointer, and therefore use 20,000 ohms for every volt measured. Electronic servicing requires meters that do not take any appreciable amount of current from the circuit being measured. So vacuum tube or transistor voltmeters with extremely high internal resistance are used. Voltmeters used for servicing aircraft electrical systems usually have several voltage ranges. Always set your meter to a range above the anticipated voltage. And while the meter is reading, change the selector until the pointer indicates in the middle third of its scale. Ammeters are installed in series with the load, and a low resistance shunt is placed in parallel with the meter to bypass the majority of the current around the delicate meter movement. The main circuit ammeter in an airplane is essentially a millivoltmeter that measures the voltage drop across an accurately calibrated shunt. The shunt is a very low resistance resistor through which all of the load current flows, and in most modern aircraft is inside the meter case. Ohm meters are handy measuring instruments having a self-contained voltage source. They measure resistance by the amount of current a known voltage will force through it. Ohm meter scales are nonlinear. That is, the numbers are bunched up on the high end. Always select a range that gives a reading in the center third of the dial. Select the range you need, short the test leads together, and move the zero adjustment knob until the needle reads opposite the zero mark. Then place the unknown resistor between the test leads and read its value on the resistance scale. Multiply by the value shown on the selector switch. When making a resistance measurement, be sure there is no power on the circuit. High values of resistance, such as ignition harness leakage, may best be measured with a megometer, which has a built-in high-voltage power source. Now, the high voltage will break down a weak lead, which might check good on a low-voltage ohm meter. Question: is an ammeter placed in series or in parallel with the load being measured? In series. Electrical measuring instruments are delicate, precision devices, and they are only as good as their calibration. All instruments should be periodically checked for accuracy by the manufacturer or by some shop approved by him. This concludes Part 1 of Basic